All right, welcome. Today is Monday, January the 4th. Happy New Year to all of you, both here and watching this exciting video online. We are ready to start in now on the next phase of where we are. Now, we are a little behind on the overall schedule of things based upon because of the COVID and all the different things, but we're gonna need to kind of pick up the pace and just kind of get rolling here. So when we look at, we've talked about atomic structure with protons, neutrons, and electrons. We've talked about the stability of the nucleus with radioactivity. We've talked about electrons and how electrons are arranged with your 1s, 2s, 2p, and all of that. And we've talked about the periodic table and how it's arranged. All of that is a foundation for what's really the fun part of chemistry, is why and how do things bond together. What, when you bring them together, that's when you have fire, you have explosions, you have all the chemical reactions that make the wheels of the bus go round and round and make us be able to function. And so we want to kind of look at those things and just kind of see how do things bond, okay? So when we're talking about ionic bonding, okay? In ionic bonding, what is an ion? What would be the definition of an ion? Anybody? We've talked about it before. We talked about it with electrons. What are the two types of ions? Cations and anions. And what is a cation?
Positive charge.
It's got a positive charge. What's an anion?
Negative charge.
So what's the definition of an ion?
Different charge atoms.
Well, it's an atom or a group of atoms that have a charge. Okay? And how do they get those charges? How does a cation become positive?
It loses an electron.
It loses electrons, one or more. How does something become negative? Gains one or more electrons. So ions are all made by the gaining or losing of electrons. And then just to kind of continue on, based upon what we've learned already on the periodic trend, looking at this periodic table here, okay? If we look at the halogens, what group number is the halogens?
17.
17. We look at the halogens, how many electrons do they want to gain or lose?
They want to gain one.
They want to gain one, okay? So Sam said that, so somebody else tell me. Madison, why do they want to gain one?
Because if they get one more, they'll have a full octet.
They get that filled octet, they get that noble gas configuration. So everything's going to gain and lose the easiest way to get to that filled octet. That's the driving force of all these chemical reactions, is trying to get that stable noble gas configuration. So things are going to gain, lose, or share electrons, ionic bonding, covalent bonding, in order to be able to get that filled octet. Okay? So, you already had right there. So the result, when sodium and chlorine combine to make sodium chloride, what happens? What does sodium want to do?
Lose an electron.
Lose one. What does chlorine want to do? Gain one. So what happens?
Sodium loses this one. Or they
Sodium gives an electron to the chlorine. Sodium becomes what charge?
neutral.
No. Once sodium loses an electron, it becomes positive. Chlorine gains the electron, becomes, and what do we know about opposite charges? They attract one another. So the ionic bond is actually, very fancy word, the electrostatic attraction between the two ions. Okay? So it's the transfer of electrons. I need to look. Where did I put? I just want to make sure I'm following along with you guys. Well, I only put it through, but no, I don't. Okay, so when you look, it's the result. How are ionic bonds formed? It's the result of what? What happens to electrons?
Trading?
Trading, let's go with a different word though, but close. Let's say it's the transfer of electrons. Okay? So then that bond is the electrostatic attraction. What does that word sound like, electrostatic attraction?
Electromagnetic.
Electromagnetic radiation, electromagnetic, okay? But electrostatic, say it backwards.
Attraction, electrostatic.
Well, just the static electricity, electrostatic is static electricity. What's static electricity? Give me an example of static electricity. You guys know what I'm talking about, right? You've heard the term static electricity before?
I don't know what it is, but like, when you go on a trampoline and your hair like.
That your hair sticks up on because it just gets off, or you have a balloon stuck to your shirt, or you take the socks out of the dryer and you can kind of hear them kind of crackling as they're kind of stuck to one another. And so that's the static electricity. In this term, in this sense, so the word static means stationary, not moving. Okay? If something is static, it's just staying the way it is. It's not changing at all. So an electrostatic attraction is the fact that sodium is positive, chlorine is negative. They have those charges that are permanent, and then they just stick together because they're opposite charge. Now, when you're on the trampoline, just so you know, you're on in your socks, and you're rubbing electrons. Now, I don't know if you're rubbing electrons onto you or off of you. I'm pretty sure you're rubbing electrons onto you. And your hair, being so fine, they're all getting the same charge. So electrons are going to all of your hair. It's going filling your body up with all these extra electrons. So the negative and the negative are repelling one another. So your hair tends to kind of go out away from each other, kind of look crazy. But then you can have, I used to do this with my son, have shock wars. Try and get, touch them to where you can shock them when you're on the trampoline, because, if you touch the metal part, you get shocked pretty good on those, okay? But that's just the electrons transferring back and neutralizing everything out, okay? So, ionic compounds are also known as salts. That's an old school name, so we know table salt, NaCl. But there's also, Epsom salts, magnesium sulfate. Salt substitute is KCl, potassium chloride. Any ionic compound is going to be called a salt. Okay? So, how do they get formed? Okay? It's going to be metals with nonmetals. Metals on the left of the periodic table, nonmetals on the right. So, you need to we have it kind of on there, but sodium has, how many electrons does sodium have? 11. But how many valence electrons does it have?
2. No, sodium?
Sodium.
1.
Just one, right? So sodium, so we just put one dot. You guys did this, I think, in 8th grade. You put the one dot for the sodium. So how many valence electrons does chlorine have? 7. So this is what you need to change a little bit. So chlorine has the 7. So it's going to look like this. Okay? So on the notes, we couldn't put in the dots above and below. So chlorine needs to have 7 dots. Each dot represents a valence electron. So make your chlorine look like this, and your sodium's already looking like that. Okay? Now, what's going to happen? When you put sodium and chlorine together, what happens?
Ionic compounds.
I know, but what in terms of electrons?
The electron from sodium transfers to chlorine.
This electron goes to here. So we end up with the sodium with what charge?
Positive.
Positive, and the chlorine with the extra electron being negative. So it's a 1-to-1 ratio. Now what about magnesium? How many valence electrons does magnesium have? 2. Okay? And you put that with chlorine. Well, the magnesium wants to lose both of these, right? So how many chlorines can it react with?
Two.
2. So one of the electrons goes there, one of the electrons goes there. So we're gonna end up getting, now look, it's gonna be Mg is gonna be what charge?
2 plus.
2 plus. And the chlorine is each gonna be minus, but the chlorines are gonna be on opposite sides because the negatives are gonna repel. But we'll say the formula of this is MgCl2. This one is NaCl. We don't include the charges in the formula, but that's what's happening. Right? You guys learned most of this in 8th grade, didn't you? It's kind of coming back to you a little bit. Maybe, kind of, sort of. Okay, so they gain or lose electrons to get that noble gas configuration. What about if we just did one more? What if magnesium combined with oxygen? How many valence electrons does oxygen have? 6, right? It's gonna look like that. So how many more does oxygen need? 2. So what's the ratio gonna be? 1 to 1, because it's gonna give it here, it's gonna give here, and we're gonna end up getting Mg 2 plus, and then the oxygen 2 minus. But the formula is just gonna be MgO. We're not gonna say Mg2O2, just MgO. Now, what we need to understand though, is that there's no such thing as an NaCl molecule. Okay? No such thing as MgCl2. That ions, the positive and negatives, they're gonna surround one another and they're gonna make these large crystals. Okay? They don't form molecules, but they form crystals. So when you look at a grain of salt, it's really billions and 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 billions of these ions all stuck together into one salt crystal. So when we look at NaCl, it's going to be an Na plus surrounded by a Cl minus, surrounded by an Na plus, surrounded by a Cl minus, and you can see it's just going to go on and on and on and on and on. So this is just 2 dimensions. The reality is that you're going to have a Cl minus in front and a Cl minus behind too. So you're going to have each, and you can kind of see it, each one of these, I've got to stay in front of the camera. Each one of these is surrounded, okay, if you get to the inside, each one is surrounded by 6 other things, the front and back, top and bottom. Okay, so it's surrounded by 6 different ones. So each Na plus surrounded by 6 Cl minuses. Each Cl minus surrounded by 6 Na pluses. We say that the formula is NaCl, that's just the ratio of the ions in the crystal. Okay, we call this the formula unit. I don't know if that's on those notes. The formula unit. We're going to treat it just like a molecule, but we just can't call it a molecule. We did that when we were talking about molar mass. I talked about that a little bit with ionic compounds. They don't form molecules, so the formula mass. So in that space in G, this is what you're supposed to draw right here in that space in G. Just show the crystal. The Na plus surrounded by Cl minus surrounded by Na plus. I'd start in the middle and then just work your way around it like I did. Yes, ma'am.
So they do not form,
They do not form molecules, but form large crystals instead. The large crystalline solid composed of oppositely charged ions, where each cation is surrounded by anions and vice versa. Okay, that's what you're kind of showing in that picture. Positive surrounded by negative, negative surrounded by positive. Okay, so one of the characteristics of ionic compounds is we don't have a molecule, we have these large crystals. They're going to be solids. They have high melting points. Okay, they're held together by strong electrostatic attractions. Now, I'm going to give you a synonym for this. These are sometimes called Coulombic attractions. I'm going to explain why it's right now. Coulombic attractions. Coulomb's law applies to anything that has a charge. Protons and electrons, the electrons to the nucleus, okay, a balloon to your shirt when you're rubbing it, anything that has charges, we're going to apply Coulomb's law to where we're going to say that the delta H of dissociation, this is the energy needed to break ions apart. Okay, and that really means to melt. Melt the ions. Because that's all you're doing. When you melt salt, all you're doing is breaking the ions and letting them roll around one another. You're breaking the ionic bond. Okay? So Coulomb's law is a measure of that energy. How much energy does it take to dissociate, to break them apart? Well, it's equal to some constant K, which you don't have to worry about, and that's not in your notes, so you need to add that K in, times, is it a Q or an N?
N.
N. N plus times N minus all over D. Now, N plus, what do you think that is?
Cation.
The charge on the cation. What's N minus going to be then? Charge on the anion. So what's D going to be? D is going to be the distance between the ions. Okay, we're going to use periodic trends for that. We're never going to actually plug numbers into this. This is going to be kind of just a comparison, but we can compare how strong are the ions held together using Coulomb's law. Now, review periodic trends. What happens to the size of the atoms as you move down in the family? I heard both. Going down in the family. What's happening to the number of energy levels?
There's more and more.
There's more and more energy levels, right? So that means it's getting bigger and bigger and bigger going down. But within the same row, going left to right,
Smaller.
that's when it gets smaller. Because the electrons are all going the same energy level, but you have more protons pulling it in tighter. Okay, so we got to remember the size. Bigger going down, smaller left to right. So bottom left on anything, bottom left is always the biggest, top right is always the smallest. Okay? That's what we're going to use to determine the distance. And this makes sense, y'all. You've all heard the expression, long distance relationships are hard to maintain. The farther apart you are, the weaker the attraction is going to be. So atoms that are small and close to one another are going to be strongly bonded, whereas those that are bigger and farther apart, then they're not gonna be attracted as much. It's gonna be easier to break them apart, easier to melt them, to dissociate them. So, okay, so if we were to compare NaCl with MgCl2 with MgSAl2S3 and then AlP. All of those. So here's a bunch of different compounds. I want to know, okay, well, which one do we think is going to have the highest melting point? Which one do we think is going to have the lowest melting point? Well, I'm going to look, the two things I'm going to look at is the product of the charges, which is in the numerator. So as these numbers get bigger, what happens to delta H? If these numbers are getting bigger, what's going to happen to this number?
Bigger.
It's going to get bigger, right? But if D gets bigger, what's going to happen to H? Get smaller. Because the farther apart they are, the weaker the attraction is going to be. And the less energy it's going to take to break them apart. So, I look at the product of the charges. So what's the charge on sodium and what's the charge on chlorine?
Okay, +1.
+1 and -1. So my product of the charges, and we just take the absolute value, is 1. Okay? But what's magnesium's charge?
+2.
+2 and still -1. Because again, it's just going to be Mg attracted to a Cl2+ to a Cl- to a Cl-. So we're measuring the strength of that right there. Okay? So it's the Cl- don't join together and make it like 2-. You just look at the charge on each individual ion. So here the product is 2. What about Mg and S?
+2 minus
+2 and -2. So the product is
4.
4. Here it's +3 -2. So now we're at 6. +3 -3. We're at 9. So they all have the electrostatic attraction. They're all positive to negative. But you guys all have refrigerator magnets, right? That's my thing. When I go to a different place, I like to get a magnet so I can kind of keep track of where I've been just with the magnets on my fridge. Okay? Luckily, my fridge is getting pretty full. I've been very blessed, been able to travel. So, you got the ones that are weak that might hold up a piece of paper, on there, single, okay, I got to remember this little note, I got to remember to do this, or a grocery list or something. But if you want to put a little bit heavier picture or even a calendar on your fridge, you got to have the Mac Daddy strong magnet, right? Because the little ones, it's just going to slide right down. It's not even going to hold. So they're both magnets. They both have the north and the south pole. They're both charged, but some are stronger than others. That's the way we're talking about here. We're measuring the strength. How strongly bonded are they? They're all got positive to negative, but this one is going to be 9 times stronger than that one. Okay? Product of the charges. So we're always going to look at that first. But what if we compare LiCl to NaCl to KCl to RbCl? Now, what's the product of the charges for each one? Notice I went lithium, sodium, potassium, rubidium, right down group 1. So those charges are all going to be what? +1.
minus.
It's all +1, -1, +1, -1, +1, -1. So now the product of the charges is a tie. So now is when we're going to look at, well, which one's bigger, which one's smaller. The biggest one is going to have the lowest melting point. The smallest one is going to have the strongest attraction, have the highest melting point. So, which one is the biggest and which one's the smallest?
The rubidium is the biggest.
This is the biggest.
Lithium's the smallest.
This is the smallest in terms of the ion. Okay, so what about melting point?
higher to,
This is the highest, right? Is that what you said? This is the highest. This is gonna be the lowest. Okay? Now that's not anywhere in your notes, but I strongly recommend maybe you copy some of that stuff down. Okay, just good examples, and if you need to just, go, did I do front and back? No, I did 2 sheets, so you can use the back. Oh, that's a good idea, I need a drink. Trying to get healthy, New Year's always, so I'm trying to give up my Diet Mountain Dew. I'm only day 1 and I missed it big time. So these are just good examples here. So this is going to have the highest melting point. This is going to have the lowest. Y'all follow me on that? So that you don't ever have to put in real numbers on this, it's all relative. You look at the product of the charges first, and then you look at the size of the ions last. So, one more example. If we say NaCl, MgCl2, KCl, and CaCl2. Okay? Just take a second and think which is going to have the highest melting point, which is going to have the lowest melting point of these 4.
magnesium chloride is gonna have the highest.
Oh shoot, this is a 2. So this is going to be +2 -1, +1 -1, +1 -1, +2 -2, -1. Okay, why Sam? Why magnesium chloride?
Cause it's a smaller ion magnesium is, and it's closer, like that and chlorine are closer than sodium and chlorine. Magnesium and chlorine are closer than
Okay, so the chlorine is the same in all of them, right?
Mhm.
So the first off, if we want the highest melting point, which 2 can we eliminate immediately as far as that's concerned?
the
NaCl and KCl, because the product of the charges. So we know that the highest one has to be one of these 2. So now we have to, since it's a tie with the product of the charges, we have to look at the size. So, which is bigger, magnesium or calcium? Calcium is bigger, so magnesium is the smaller one. So when you plug that into here, the smaller the value, the larger this is going to be. So you're absolutely 100% right. Magnesium chloride would have the highest because it's got the greatest product of the charge and it's the smallest distance between the ions based on the periodic trend. So this has the highest melting point. Which one's going to have the lowest?
KCl.
All right. So again, we know it's going to be one of these 2. Why KCl?
Cause it's a bigger ion.
Because K is bigger than Na, which makes this distance bigger. The bigger this is, the smaller this is. So KCl, whatever over here, KCl is going to have the lowest melting point. Y'all seeing how I'm doing that? You look at the product of the charges, which we get from the periodic table, and you guys all seem to be pretty good with that. Greater product of the charges. We look at that first. Whichever one wins that one is the outright winner. If it's a tie, you go and you look at the size, and you just use periodic trends to determine the bigger or the smaller. See, this is why chemistry gets to be a challenge, because we're gonna, we thought, oh, we did periodic table last semester, we're not gonna have to deal with that anymore. But we learned all that so we could build on it. We learned about electrons so we can see how they're gonna get transferred. All right? So, I don't know where it's going, the fill-ins down here. It says, the greater the product of the charges of the ions in an ionic compound, the greater the attractive forces, the higher the melting point. Is that all written in for you, or you did?
A and B are.
Okay. So, and then the bigger the ion. So that's just in words explaining what we just did. Okay? Now, ionic compounds, another property is they do not conduct electricity in the solid state. Oh, I don't have anything. Okay, those of you at home watching this energetically, enthusiastically, you're gonna be able to fast forward through this part because I gotta run and go get some salt. Okay, this is just some rock salt. Now, when I have this plugged in, why is this light bulb not on?
Because there's nothing magnetic in close to it.
No, it's not magnetic. Well, how does this light switch work? Lights are on, lights are off. What's the thing that the switch is doing?
Allowing electricity to go.
Allowing electricity. You gotta have a closed circuit in order to have electricity to flow. So when we look at this one, it's an open circuit right here. But if I close that circuit with another piece of metal, the light bulb comes on. Okay? So we have an open circuit between here. So if we can get electricity conducted between those two, then the light bulb will come on. So if I take just some salt and I stick it up onto here, okay, it doesn't conduct in the solid state. But, I need a beaker and I don't have the right beaker. I almost always have one. Oh, here, I can use this one. Get the critters out of it. Okay, I put it in some salt into the water. Oh. Just get it to dissolve a little bit. Now, when I put it in here, the light bulb comes on. So, solid ionic compounds do not conduct electricity. So, is the definition of electricity? No, that's not given. So we need to write this in the margin. Electricity. In order to understand the why, we have to understand what it is. That's a lousy why. It's the flow, purple, of charged particles. And those particles can either be electrons or ions. Okay? Electrons or ions. So right now in the wires, we're going to learn about this probably tomorrow. In the wires, the electricity is flowing, the electrons are flowing through the wire. We're going to learn that in metallic bonding. It allows for the flow of electrons. But with salt, when we put this into water, when we put salt into water, we come in here, what happens is that when it dissolves, it's going to pull this away, and then it's going to completely surround it and pull it into water looking like this. And then the Na plus gets surrounded by the other part. That's not a water molecule. Like this. So they dissociate, they break apart from one another. So when we put the salt, it disappears because the big crystals, the billions and billions and billions and billions and billions of ions that are all packed together, make it big enough for us to see, have now broken apart into individual ions that are way too tiny to see. And so they're just floating around in the water like this, and Na plus and Cl minus is floating around, completely surrounded by the water molecules. But now we have ions. In the solid state, you have charged particles, they just can't flow. They can't move. But you put them into water, or you melt them, you break the ions apart from one another, that allows them to move, and they conduct electricity, and we call those things electrolytes. When have you ever heard the term electrolyte?
Gatorade.
Gatorade, right? Do you know what an electrolyte is?
I knew it was like some type of like salt.
Some type of salt. Gatorade is the most brilliant marketing that I can think of strategy. Because when you sweat, we all know that you sweat out salt. If you've ever tasted your own sweat, if you know it's running down your cheek or whatever, you lick your lips, you taste the salt. If you play baseball or anything out with a cap on, like I play tennis, you get wringing wet, sweaty, and then it dries, you can see the salt lines on the cap. You know what I'm talking about, okay? Maybe even sometimes in your clothes, on your shirt, if you really sweat it and then it dries, you can kind of see sometimes the salt, you can just kind of see the buildup. So you have to replace the salt, otherwise you start cramping up. But salt, sodium, has such a bad nutritional reputation these days that even though your body needs it, everybody says, man, sodium's bad for you, sodium's bad for you. Well, no, your body needs sodium. Your body needs the salt in order to be able to function. So rather than saying, hey, buy Gatorade, it's full of the salt that your body needs. People say, oh man, it's got a bunch of salt in it, it can't be good for me. So instead they say, hey, it replaces the electrolytes that your body so desperately needs. Well, the electrolytes are nothing more than the salts, the ionic compounds that are dissolved in there to replace all the salts that you just sweated out. But again, people have that bad connotation of the sodium, so they just, electrolytes. What's an electrolyte? I don't know, but my body needs it. You know? And so it's a great marketing ploy, but it's really saying, hey, Gatorade's just got all those salts in it that your body needs. So, an electrolyte, I'm giving you, this is going to be another term here for you. Oh, I gotta get, shoot, I'm not gonna get through. Too much good stuff here. An electrolyte. It is a substance that dissolves as ions and enables the solution to conduct electricity. So what would a non-electrolyte mean? how would it have to dissolve? As charged or neutral?
Neutral.
It dissolves as neutral. A substance that dissolves as neutral molecules. And we'll talk about that. This is more covalent substances like sugar. As neutral molecules, so the solution does not conduct electricity. Neutral molecules versus ions. Okay? So electrolytes versus non-electrolytes. Now, quickly, if I take this salt, okay, I have the salt on the table. Need something hard. And I take this plastic cup and I just smash on it some. What happens to it?
Breaks up the chunk.
Is it going flat? Is it malleable or ductile? It's brittle, right? We can explain that again with the positive and the negative. Because when I go and I hit that, I'm shifting this, and I'm gonna make, if I try to just pull this way, it's very hard to pull apart. But if I twist it just a little bit, it comes apart real easily, because what's happening when I twist it?
You're just making a smaller.
You're moving once.
So instead of the blues being next to the greens, the green is next to green and blue is next to blue, right? The same charges, what do we know about like charges? They repel. And so rather than it sticking together, they're repelling from one another and it shatters. So when you're breaking when you're smashing a salt crystal, all you're doing is forcing positive and negative and positive and negative next to one another. So positive next to positive, negative next to negative, just the shift. So ionic compounds are brittle. They're not malleable or ductile because you force positive ions next to one another. Okay? And we already kind of talked about this. We already know water is very polar. What does it mean that a molecule's polar? No, we don't know that yet. That's the end of this chapter. Okay? Water has a positive and negative end. It's a neutral molecule, but it's got a positive and negative end. The electrons aren't shared equally. So you can see that on the green one, it's attracted to the white hydrogens. The blue one, the positive, is attracted to the negative oxygens. And so they're attracted to one another, so that makes them very soluble. Ooh, I thought I had another minute or two. All right, we'll pick that up tomorrow, so you're gonna have to, you get to watch the video tomorrow.